Angel. Welcome back to Decaf-Math ASMR. And a very warm welcome if you are new here. It is wonderful to have you join me here today. Today, let's take a look at 3 questions that involve cross multiplication, or rather where you can use cross multiplication to help you solve them. Of course, there are always multiple ways to solve something, but cross multiplication is going to be our theme for today. Cross multiplication, not to be confused with cross canceling, which I always mix up the words, but cross canceling is for fractions. Cross multiplication is often used with proportions, solving proportions. So the 3 questions that we're going to look at today are going to get increasingly complex, just algebraically. Our first one is just going to be a basic proportion, and then we'll include an x on both sides, and then our third one will involve some foiling and some factoring and all that good stuff. So we're going to have some good review and some fun and just some relaxing and learning, okay? So let's start with the basic proportion question so that we can actually build some intuition about why cross multiplication works. So let's take a look at something like, let's see, how about 2/3 equals x over 15. So like x is our thing that we're solving. So we have a proportion which is just about setting ratios equal to each other. So 2 to 3 is equal to something over 15, or 15x to 15. So we can write ratios in different ways, but one way is to write them as fractions like this. So mathematically speaking, we're basically solving this ratio or this fraction. So what number over 15, when I simplify it, gives me 2/3. But, a lot of times proportions are related to word problems or something that we're trying to solve in general. It's not always written out directly like this. So we're just going to translate it into something like this where we're solving for x. Now, from here, you may have learned this, I assume, if you've heard of proportions, that you've also learned to solve for x directly here just by a one-step motion, which is to multiply by 15 on both sides, which would give you 15 times 2/3, or 2/3 of 15 equals x. If you've never heard of this before, don't worry about it, but I just wanted to mention that so you don't have to jump into cross multiplication just because I said so in the beginning of the video. You can still just go ahead and solve this with one step. So in this particular case, cross multiplication might seem kind of overly complicated, but it's good to still build some intuition. It still works, but I just wanted to show you that there are multiple ways to solve something. So one is to just multiply by 15. The other is this idea of multiplying terms that are across from each other and setting them equal. So you might see this. So we have 3 times x and 3 are across from each other over this equal sign. So we'd have 3 times x, set it equal to 2 times 15. So you'd have 3x equals 30. 2 times 15 is 30. Then divide by 3 on both sides. So again, the one step. But then you'd have x equals 10, because 30 over 3 is 10. And it's always good to check this kind of stuff. So if you put in 10 over 15, we can rewrite that as 2 times 5 over 3 times 5. And the 5's cancel. So in other words, you can divide by 5 on the top and the bottom here, and get 2 over 3. So if it helps you to kind of look at simplification this way, you would basically have 2/3 times 5 over 5, which is 1. So anything times 1 is itself. So that's the real reason. But if you can find a number that divides, that goes into both of these, then you can cancel that out. So we have 2/3, so that works. So in this particular case, like we said, you could have just done one step initially. Here we end up doing a one-step situation anyways, so it doesn't actually simplify things, but this is a great place to start because this will help us think about what happens when we want to generalize this. So of course cross multiplication will come in handy if we have x's on both sides, or like in the next question we'll take a look at it. But here let's look at this general form and show why it works first, just to get an idea. So let's say we have like a over b equals c over d. Now we're getting very general. So that's kind of the form that we had before. 2 over 3 equals x over 15. So, and now if we prove this in general, then a and b and c and d can be anything. They can be expressions, functions, numbers. Numbers are functions, that kind of thing. We can have it be whatever we want. Conceptually, it all works and it's all the same. As long as we don't break math, of course. We can't divide by 0, and we want things to be within a domain that works, right? But assuming that's all good, then all we're really trying to show is that a times d equals b times c, or c times b. The order doesn't matter for multiplication, but we're going to multiply terms that are across from each other. And in this case, it's not even necessarily terms, because a and d could be placeholders for expressions, but we multiply the thingies that are across from each other. So a times d equals c times b, or b times c. Let's just go ahead and do bc like that. So that is what cross multiplication is about. So sometimes multiplying them like this gives you something that is easier to work with, and then you can solve this. So let's look at why this is true. If this is true, then this is true. Let's look at why that's the case. Really, it's just one step of algebraic manipulation. So let's look at our a over b equals c over d. So one thing we can do is notice that we have b and d on the denominators here, as if we think of them as fractions. And so they can be expressions too. They can be rational expressions, but we have b and d in the denominator. So one thing I can notice is that if I multiply by bd on both sides, meaning b times d, again, because we have this equal sign, when you have something equals something, if you do something else to it on one side, you have to do it on the other to keep the expression equivalent, right? So if you have 5 equals 5, and then you multiply by 3 on one side, so that you get 15. 15 isn't equal to 5, 15 is 15, so if you multiply by 3 here, you have to multiply by 3 here. It's like a balance, right? Keeping things in balance to find an equivalent equation. So in this case, because I noticed that b and d are in the denominators, if I multiply both sides by b times d, what's cool about that is that if I look on this side, b times d, and I have a b here, b times d is like a b d over 1 if it helps you to look at that way for fractions, but we have bd and we have a b here, so we can cross cancel the b's, right? And we're left with the d and d over 1 if that helps, but we just have d times a, because I put it over 1 because with fraction multiplication you usually multiply across, so d times a over 1, and the b goes away, so just 1, but anything divided by 1 is itself. So d times a equals, and then here we can put it over 1 again if that helps, CBD over D times 1, which is D. But we can do the cross canceling, so D and D go away. Anything divided by 1 again is itself, so we have C times B. And so we have DA and AD are the same. For multiplication, it's commutative, which means the order doesn't matter. So 2 times 3 is 3 times 2. So this would be AD equals BC. We can just flip each side to get what we were looking for here. So that's it. The idea is simply to multiply BD on both sides. Now let's say you didn't recognize that in the first place. That's totally fine. It does seem a little bit random. But if you know that your goal is to get something without the denominators, then it kind of makes sense, right? But let's say you didn't know that. In general, you can just do this one at a time. So you can just do this one step at a time by multiplying by D first, maybe, to get rid of 1. So you multiply by D on both sides so that you have DA over B equals C, and then you move this B over by multiplying by B on both sides. That's fine. So you have DA equals CB, right? Which is AD equals BC. So that's just the same as multiplying by D first and then B, or you can do B first and then D, or you can just do BD all at once, right? So that's it. So now we have this general formula, and I thought starting with that first proportion, even though it was a little bit, it was more complicated than it needed to be to use cross multiplication for that one, I thought that it would be the clearest, most direct A to B equals C to D kind of thing before we add in other expressions. So along that line, let's say we now have x over 2 equals 7 over x. So this is our second question with cross multiplication. Again, here we're going to make sure that math doesn't break. We don't want x to be 0. Dividing by 0 is a no-no. In general, we can do this one step at a time. Again, however you want to do it. You can even, multiply by 2x on both sides, knowing that there's a 2 and an x here, and see what happens. So basically, you're redoing the PD thing instead of doing the cross multiplication. You can just derive it every time. But since we just talked about it as a method, we can go ahead and do this. So x times x is x squared. 2 times 7 is 14. So we have x squared equals 14. And now we just solve however we normally would. In this case, since we have x squared written like this, be careful, we have to do plus or minus square roots on both sides. Square roots undoes the squared part, but we want to have plus or minus because negative square root of 14 squared in parentheses like this is also positive 14, because negative 1 squared is positive 1. So just be careful of that. But other than that, it's just our usual plus or minus square root of 14. So x equals square root of 14 or negative square root of 14. And that is it. If we want, we can plug this in and rationalize it. Let's see if we want to check that. We might as well, right? So square root of 14 over 2, does that equal 7 over square root of 14? So you don't want to check by cross multiplying again. You'll want to just take one side and bring it to the other. So starting with this, you might as well check. So I'm going to rationalize it by multiplying by square root of 14 over square root of 14 so that I can get rid of the square root part. Square root of 14 times square root of 14 is 14. And then I divide by 7 on the top and the bottom. The top goes to 1, bottom is 2. So we have square root of 14 over 2. So it works for a positive square root of 14, and then with negative, we're just going to have negative on both sides. So that'll still be true. So you can always check with this stuff, which is really great to just plug in. It's the nice thing about algebra is you can always just plug in whatever you get to check. So that is an example. You can, again, solve by moving stuff around. You can multiply by the 2x and not even bother with cross multiplication. You're basically doing cross multiplication at that point, but you don't have to directly do that if you don't feel like it. You don't have to take my word for it if you don't want to. So then the last one, now let's do one with a bunch of algebra, just for some review anyway, but also to point out that, you can have whatever you want. You can even get fancy with like trig and stuff like that, but at that point, solving it might not always be very direct. But again, here you can multiply by 2 and times 2x plus 3 on both sides and basically derive your cross multiplication. Or you can go ahead and multiply by these two. This times this equals this times this. Hopefully the numbers work out. But we have x plus 1. I tried it really quickly on the back of a napkin, but so we have x plus 1 times 2x plus 3 equals 2 times 3. So here we have our FOIL method here to simplify this. So now we did the cross multiplication step, right? But then we want to solve for x now, so we'll FOIL. So the first terms multiplied together, x times 2x is 2x squared. We do the outside terms, so x times 3, so 3x. The inside terms, 1 times 2x is 2x. And then the last terms, 1 and 3, so that's 3 equals 6. 2 times 3 is 6. So we have 2x squared plus 3x plus 2x is 5x. And then when we solve quadratics, it's nice to have everything be like stuff equals 0. So I'm going to subtract by 6 on both sides. So move this over by subtracting 6. So minus 3 equals 0. So now we just have this quadratic equals 0. And so here we can try to factor or use the quadratic equation, whatever you like at this point. But I think we can factor this. So what we're going to do is look for pairs of numbers. So we're going to have stuff times stuff. So these are going to be binomials, so it's going to be something x and something x, and then plus or minus and plus or minus, and then some number and number. So this is our backwards foiling. And we want them so that the coefficients of the x part multiply to be 2x squared. So it's either going to be 2x and 1x or 1x and 2x, but we can just switch these numbers so that it's lined up. So we can just pick one. So we might as well do 2x and x. And then we want these two numbers to multiply to be negative 3. So that would be 1 and negative 3, or negative 1 and positive 3. 1 and negative 3, or negative 1 and positive 3. And so from there, we're just trial and error. We're going to want to get the number so that the outer plus the inner gives you 5x. So in that case, since it's plus 5x, I'm going to have plus 3 here and minus 1 here, because when I do the first, I already took care of the 2x squared. When I did the last of the FOIL, I already took care of the negative 3, but the oi part of the FOIL is outer and inner. So outer is 6x minus x is going to be the plus 5x. So there's a bit of, guessing and checking, but in this case, since 2 only has 2 and 1, and negative 3 is just switching which one's negative or positive, but it's also prime. I picked the numbers so that they're kind of nice. But we can check this and FOIL it back out. We should get this. And now, since it's factored, we can go ahead and use the zero product rule. So that just means in order for this thing times this thing to equal 0, either this thing is 0 or this thing is 0, or both, because if these are not 0, they can't multiply to equal 0, because 0 times stuff is 0. So that means that 2x minus 1 equals 0, or x plus 3 equals 0. And this is just a bit of review, but if you cannot factor it, you can just go ahead and use the quadratic formula. The negative b plus or minus square root of b squared stuff. Yeah. Okay, but in this case I picked it so that we can. And so now we just solve each of these individually. So we can add 1 on both sides to get 2x equals 1, then divide by 2 on both sides, so 1/2. And then here we subtract by 3. And if the algebra is overwhelming, don't worry about it at all. I'm just assuming that we've learned a bit of this stuff, and I thought that it would make for some good review. So our answers are -3 and 1/2. Okay, are you ready to erase this? We're going to just quickly check over. It's always a good idea to plug back in just in case you end up with the denominator of 0 or something and you want to eliminate one of the answers. You ready? Okay, good. So we're just going to check the numbers really quickly, make sure that it's all good with 1/2 and -3. So I'm going to go ahead and copy the question again. Alright, so let's try out 1/2. Let's just check it. So 1/2 plus 1 over 2. You always want to start on one side or work them separately, but then make sure they're equal. But you don't want to just like go left to right and just say it is equal, because that's what we're trying to check. So equals question mark 3 over 2 times 1/2 plus 3. Let's see if this is true. So for 1/2, we have half plus 1, which you can write a common denominator and write it as 2 over 2. So that's 3 over 2 over 2, which is 3 over 2 times 1/2, which is 3/4. So this side is 3/4 when I plug in 1/2 to this thing. This side I have 3 over 2 times 1/2 is 1, plus 3 is 4. So we do get 3/4 on both sides. So that's good. Thankfully, yay. It's always really nice when it works out. And then I think -3 will be nicer to work out because there's no fraction. But we can have -3, so let's check -3. -3 plus 1 over 2 is -1. Right, -3 plus 1 is -2, divided by 2 is -1. Does that equal to 3 over 2 times -3 plus 3? And the answer is yes, because this is 3 over -6 plus 3, which is 3 over -3, which is -1. Positive divided by negative is negative, so we get -1 on both sides. So that's also good. So we are happy about that. Okay, so this was the messiest, I think, algebraically, because we had to FOIL out, and then we had to rearrange stuff and then factor again, and then we got 2 answers, and then we had to go back and check them. But that is my point. Sometimes cross multiplication can save you a lot of time, and sometimes you don't really need it at all, and sometimes you can just not even bother with a method if it just seems, too much anyway. You want to derive, you don't even need to memorize that. You can just multiply by 2 times 2x plus 3 and get it every single time as well. So in general, that's why I like to stick with the classics around here, the basics. I like new methods and shortcuts, but I think that math is a universal language, and it's also a timeless language. So the more of these little tricks, over the years, people will say like, flip and switch, or the AC methods, or the tabular methods, or whatever, for integration or whatever like that. Like, I think they're great. They save you a lot of time. But I tend to start with the basics around here first, before we start noticing little shortcuts, because, they should all be rooted in logically something that sticks, or something that we can, because the things we can always go back and prove and come up with the shortcuts. But if we only do those shortcuts, then down the line, 10 years from now, 20 years from now, you might forget or not even remember, like, what was I doing for that? But if you remember, for instance, foiling is, or factoring in this way for quadratics, is to try to work out the backwards of the FOIL method, and you generalize what FOIL looks like, then you can kind of piece together, rather than me saying, oh, factor this first thing, factor the second thing, try out all the pairs, to really break that down step by step. I think that's always the best thing to do, and then as we practice it, we get better and better. So that's just my 2 cents, though. Always find what works for you and what you like, and what your what your preference is as you study and learn things. But anyways, I hope that this was interesting and maybe boring for you. Maybe you're asleep by now, but it was fun to kind of chit-chat over some math. So thank you for joining me. I will see you around for more math very, very soon. And let me know if you have any particular questions about this